This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, welcome everyone to Lecture 26. And where are we at? We were considering metastability last lecture, and we're going to keep talking about that, and I'll show you some, I think I'll show you some spice simulations, etc. So, we made an RS latch using two NOR gates. And normally I had one on top, one on the bottom in a crisscross configuration, but you can also redraw them this way. I'm too loud for myself here. And we want to try to understand how we can enter into a metastable state today. And so I've just redrawn what we had last week was this picture. So I think that was R, that was S, that was Q and Q bar. And I've just drawn the same thing, but moved one around to the other place, reset there. And let's consider the situation when S is naught, R is naught, and Q is naught. Remember when set and reset are both 0, it should just remember its current state. So if I set Q to be 0, then this should be a stable configuration, and we can double check that. So naught and naught, if we NOR them together, the output should be a 1, and naught and 1, putting into a NOR gate, the output should be a 0, so this is consistent. So this is a stable configuration, having S naught, R naught, and Q equal to 0. And we want to think now about how we can put this into a metastable state. That'll be the next slide. So we start off with S0, R0, Q0, that means that this guy's a 1. In fact, let me now label them not digitally but with a voltage. So this will be 5 volts here. And the other configuration, the other piece of information we need to keep in mind is that the input to this logic gate here looks like a capacitor, and the output of this logic gate here looks like a resistor. We want to keep that in mind as well. So when Q's naught, I've got 5 volts in here, that's this line here. When S goes from 0 to 1, so I'm going to put a pulse into the set pin here. When S goes from 0 to 1, the voltage here, that was 5 volts, it begins to discharge. Why? Because the voltage here appears across this capacitor here, serving as the input to this gate. When I change the input to this gate, its output is going to be some FETs, and they have a resistance. So the output of this gate has got some resistance, and it's trying to pull the voltage here to 0. Because if this were an ideal gate, the output here, when S goes from 0 to a 1, and this guy's a 0, then its output needs to change from a 1 to a 0. Because that's the truth table for a NOR gate. In other words, when S changes, the output of this gate has to go from 5 volts down to 0 volts. The way that's physically achieved is that a FET is going to turn on, connected to ground. So this guy here will have an N-channel FET on the bottom. It turns on, trying to bring this voltage to ground. But there's a resistance from drain to source. That's this resistor here. Over here, this input gate, the input's going to go into one or more FETs. And that looks like a capacitor. If this was at 5 volts, that means that these FETs here on the input, they've been charged up to 5 volts. So when this gate switches, I have to discharge this capacitance here. I have to bring it down from 5 volts to 0 volts. Any questions about that? Okay, so I've done that part. Keeping in mind that if these gates are pretty much ideal, then, so on the one hand, 0, 1, 0 is a stable configuration, 0, 1, 0, that's stable. Oh, sorry, I'm drawing it the wrong way for you. So let me do it properly. Set, reset, Q. So set, reset, Q. Oh no, that's not what I want to draw, sorry. What I want to say is that when S and R are both 0, then this guy looks like an inverter and this guy looks like an inverter. So when S is 0 and R is 0, I have got two inverters connected back with a feedback loop. And so what I was trying to say here before I got ahead of myself is if I've got 0 volts here and 5 volts here and 0 volts here, that's a stable point. If I have got instead 5 volts here, 0 volts here and 5 volts here, that's a stable state. And we learnt last lecture that I could also have 2.5 volts at all three junctions, and that is also an equilibrium point. And so remember what we have, so going back to this picture here, what we have is this was at 5 volts. When I put this pulse in here, this 5 volts will begin to discharge. It won't drop to 0 immediately. As it's dropping, it's going to pass 2.5 volts. If I could magically, at the precise moment that this passes 5 volts, bring this straight back down here, then I will have 2.5 volts here. That goes through this gate here to produce 2.5 volts. That comes back into here, and now this is 0, this is behaving like an inverter. 2.5 volts in here will produce 2.5 volts in there, and I have my metastable state. And that's how you can get these guys into a metastable state. If I had to summarise it quickly, I would say there is a capacitor between these two inverters. When I change state, I have to either charge up this capacitor for logic 1 or discharge this capacitor for logic 0. But if I were to partially charge that capacitor, I can get it stuck. Well, I can bring it to any voltage I like. If I apply a very short pulse on the set pin, I can bring this capacitor to any voltage I want. When I remove the pulse on the set pin, I go back to two inverters. If the charge on that capacitor is quite low, then when it goes through this inverter, I get a large value. When it goes through the first inverter, I'll get an even smaller value. And although I got it stuck at, say, 1 volt, it will quickly run away back to 0 volts. If I got that capacitor stuck at, say, 4 volts, it will quickly run all the way up to 5 volts. But if I get it stuck exactly halfway, in theory it'll stay there forever. And in practice, any amount of random thermal noise will knock it one way or the other, and it will then run away to the two extremes. But a short pulse can get this stuck in a metastable state. That's the key point for the first stage. We'll see later how this leads directly to metastability in D-type flip-flops, but this is the main point. Any questions? Okay. Okay, so I'm going to look at simulations of this and try to get it stuck, if I remember correctly. Remember that a D-latch, the Verilog code, looks just like this. A D-type flip-flop can be made using two D-type latches in a master-slave arrangement. So if I can get this in a metastable state, I can get a D-type flip-flop into a metastable state. You can read the rest yourselves. Let me now try to run a simulation of this. Okay, this is interesting. Here we go. Where are we? D-latch. So here's my D latch that I showed you a few lectures ago, made out of an inverter. So the lecture slides have used 2 NOR gates because then you've got set and reset. I've used 2 NAND gates here that also produces an RS latch. It's just that rather than reset, you've got reset bar, and rather than set, you've got set bar. Down here it's... Oh, sorry, I'm being silly. These are NAND gates for another reason. This is what makes up the D-type latch, as I told you last lecture, and then promptly forgot. And over here, my RS flip-flop, as I was saying before, I made them out of 2 NAND gates, which is why their inputs are not R and S, but rather R complement, S complement. So rather than putting in 2 zeros here to have this latch, you put in 2 ones here. But that's, it all works the same. So I've made this into a nice little module so I can use it elsewhere in my SPICE simulations. And I'll show you this D-latch misbehaving. So here's my D-latch, that circuit that I showed you just before. In practice, any logic gate you have is going to drive other logic gates. Rather than stick a whole inverter here, we know that the input to a CMOS logic gate looks just like a capacitor, so I just put 2 capacitors here to simulate driving additional logic gates to make it realistic. And the point here is that I have under my control what's happening at the data and the gate pins, gate or enable pin. And presumably I've chosen the timing here in a special way such that we end up getting stuck. So let's have a look at the inputs. The data pin looks like this. So the data pin starts off at a 1, drops to a 0, comes back up to a 1, drops to a 0 like that. Let's look at the gate pin. And you see, so remember when the gate is, in fact it depends which way round I've done it, but let's assume I've done it around the normal convention. If the gate is a 1, the input should be copied to the output. That's what we want. And what I've got here is that the gate pin drops just after the data pin changes. Now let's think about this in terms of capacitances inside this D-latch. When this input changes from a 1 to a 0, then the inputs to the FETs here, they have to discharge their capacitor. Well, if they're N channel, they discharge. If they're P channel, they charge. But you have to change the capacitance at the input here. That's when the gate is open. So the gate's open, the input's changed, so the input capacitances inside the D-latch, they start charging or discharging. And then suddenly we slam the gate shut, which means that this input change is no longer present on the capacitors there, and they just get stuck at the last value they were at. And so in this way, by making this gap precisely the right distance, I can get the input capacitors stuck at 2.5 volts. And then the rest of the circuit where there's the feedback loop there, well, that can maintain the 2.5 volts for a short period of time because it's an equilibrium point. That's the theory. Let's see what happens in practice. So let's have a look at the output of my D-latch. And, well, this one seems... Oh, no. Over here we see this is the metastable state over here. So okay. There's actually a difference. So between the green and the blue, that's a slightly longer time than over here, unless my eyes are deceiving me. And so over here, there is enough time between when the data changed and the gate changed for the capacitors to discharge, and so the latch worked properly. Whereas over here, there is not enough time, and so the capacitors get stuck at the halfway voltage here. They don't get stuck forever because partly I wasn't going to spend 5 years trying to optimize the time difference between here and here to get it just right, and partly because this computer uses floating point arithmetic and you'll get arithmetic errors, So no matter what you do, I don't think you can get it stuck halfway forever. Just like in real life, your flip-flop is not going to stay in the metastable state forever, even though it's theoretically possible, because any amount of noise is going to push it out there. But this, right before your eyes, is this latch entering a metastable state and then coming back out of it. And it's simply because by closing this gate very early after the input's changed, the input capacitors that have been discharging get stuck halfway. Any questions there? So while you're thinking about that, I might just expand. So if I have a D-type flip-flop, roughly speaking, the same thing happens. That D-type flip-flop, the output circuitry, is going to latch the value by basically having two inverters connected in a loop, like we showed you before, the same as this latch. It basically takes a photograph at the rising edge of the clock. It's designed so that at that rising edge, it can sufficiently charge or discharge its capacitors to make it work, assuming the input's constant. But if your input starts at, say, 5 volts, there's a rising edge of the clock, and things take a finite amount of time, it starts to charge its input capacitors, but then if the input suddenly changes from 5 to 0, it then starts discharging the capacitors. Even though it's a very short time, ideally it does it immediately, it does it over a short period of time, but if you change the input then, you can stop that capacitor from being fully charged or fully discharged. And then it can be stuck in a metastable state. So it's exactly the same principle as what's happening here, no matter how you build a flip-flop. I have a second simulation here just for fun. D-latch misbehaving 2. Same circuit, I've just changed the timing a bit. Run it. Here's the data pin, similar to before. Here's the gate pin, changing when it's shutting down. And you see here it's just on the cusp of becoming metastable. It probably doesn't reach there, but I've closed it sufficiently short that the data input changes from 1 to 0, so the input capacitors start to discharge. So the output starts to go down to 0, that's the correct value. But then you slam shut the gate, and the capacitor ends up stuck, not quite at halfway, but just above halfway. And those two inverters in a loop, they will push you back up to a 1. And so it goes back up to the 1 here, and that's what you get there. Whereas down here, I've got it just the other way. It's just long enough so that you shut the gate, the capacitor's discharged to just under halfway probably. It gets stuck at pretty much halfway for a fair bit of time, and then it falls back down to 0. So that's partly for fun, partly to show you that this is the responses you get. And we don't know whether we're going to go back up to a 1 or fall back to a 0, because it depends partly on the precise timing, and in real life it also depends on thermal noise. Here, if there's thermal noise, it might have been enough to push you down to the other side and you'd end up down there. So this is more for fun. I've already covered the main principles, but do you have any questions there? Okay. I have another SPICE simulation to show you near the end of this lecture, but in terms of D-latches and flip-flops, I suspect we're done for the moment. Okay, so I've basically told you all of this already, and I've told you that one too. Now, hopefully you've realised there's a textbook for this course and you have access to one. The library's got 20 copies or something. In that textbook, maybe the most interesting thing in there is that the authors have actually built an actual electronic circuit with a feedback loop that drives the input into producing metastable behaviour in a flip-flop. And then you can actually see this in the real world. So I use by simulations and I do it by hand. They've actually done it in hardware with a bit of a feedback loop to adjust the timing until it becomes metastable. And this green trace here, so you can look in the book for details of everything else, but this green trace here, so this corresponds to the output of a flip-flop. This would be a logic 1, this would be a logic 0. And you can see that the flip-flop really does get stuck halfway if the input changes too close to the rising edge. So this is not something theoretical, this really happens. And the textbook has another picture in there over a longer time, and you can see that the time it takes to resolve, to come out of the metastable state, changes. Sometimes you come out of it quickly, sometimes you come out of it a lot slower. Once in a billion gazillion years you might not come out of it for quite a while, but almost always you come out of it fairly quickly these days because flip-flops are very high speed. The two inverters in a loop, they have very high gain, so as soon as you're a fraction above or a fraction below halfway, you quickly run off to the extremes. So you may enjoy looking at that part of the textbook. Okay, so it's probably good to remind you of these things too. Let me just check. Okay, we'll get to that in a second. Let me shrink this, move it up there, get my doohickey here. So, if you're asked to explain theoretically about metastability, then it begins with the transfer function of this circuit here, where we break this, so that's V in, this is V out, and I've got my transfer function of two inverters, V in, V out, and it looks something like that. And for two reasons, I'm going to draw the line y equals to x here. So one reason for drawing that line is that this will show me the possible equilibrium values for this guy here. When you can put a voltage in here and get exactly the same voltage coming out, that means that this loop is in an equilibrium position. It'll stay there forever theoretically. And we see that there are three of these places, the two that we want and this metastable state here that should be halfway. I just can't draw very accurately. Now, we ran out of time last lecture, but some of you might be interested in this little graphical trick. If I want to understand the behaviour of this circuit, and because there are time delays, so I can, if you like, put in a voltage of 4, excuse me, I can put in a voltage of say 4 volts here and ask what happens. So we go down here to 4 volts. If I put 4 volts in, then what voltage am I going to get out here? Well, that's easy. I just go up to here, and that's the voltage I get coming out. Now that then gets fed in to be the new input value, because we just implicitly think there's a bit of a time delay here, so I can feed it back in and repeat the process. And the trick to feeding it back into the input is that I then draw, and actually I want to improve this diagram a bit. I want this to still be going up a tiny bit. Okay, the trick is that you've put in your input voltage, you get your output voltage here. Now, by going across horizontally to the y equals to x line, that has converted the output value. You see, this is my output value. By going across to this y equals to x line, I've now converted that to my next input value. And so therefore I now just move up to this curve here, and this will be the next output value. I'll do the same thing down here where it's a bit clearer, where we can go a bit further. If my input is 2.6 volts, which I'm going to assume is down here, then I draw, so then my output's going to be here. If I feed that output back to the input, I can either go across here, see that this is, I don't know, I'll make it up, 3.5 volts, come back down here to 3.5 volts and start again. Or the nice graphical way, the equivalent thing is to just move across to this y equals to x line, and where it intersects, that's the 3.5 volt line here. And so I then just go back up to this curve here. And then on the next iteration, I go across and back up, across and back up. And so you can see graphically that if I start close to the halfway point, then by the time I go across, back down, across, back down, across, back down, I converge very quickly to the two sides. Excuse me. And the sharper that curve is here, the faster I will converge to the two sides. So these days flip-flops have very sharp gains here. So any perturbation away from the middle, you're going to converge quickly to the two ends. That's probably all you need to know about metastability. Any questions there? If you ever do maths and look at dynamical systems, then you'll be doing pictures like this as well. When you just keep iterating a function, you've got, so if you've got xk plus 1 is a function of xk, and you keep iterating and iterating, then you can draw it pictorially like this and see what happens and see which points are stable, etc. Okay, any questions there? Good. So, this might be a metastable state as well. Okay, next part of today's lecture. So you're probably sick of debouncing because I've put it in, I think, 2 of your labs and in your project. But believe it or not, there's still a little bit more I can talk to you about debouncing. Firstly, if you haven't already figured it out now, if you press a button or move a switch and you connect the output to a crow or whatever, you'll actually see that it normally doesn't transition immediately. It'll normally ring or oscillate, or what we say is bounce. And different switches can bounce different times. There's huge variability. A few years ago I found a website where someone managed to test hundreds of different switches and report on all of them. Obviously had too much spare time on his hands, but it's a real phenomena. As you will be aware, on the DE1 SoC board, the push buttons themselves have been debounced in hardware, but the switches haven't. So one option is you could debounce in hardware, but today we're going to talk about how to debounce using digital logic only. And the basic idea is that because everything we're doing in this course is synchronous design, we've got a clock there, and we only sample the input at the rising edge. So what we're going to do is we're going to connect our button up, we're going to sample it at the rising edge of our clock, and then we have to decide what is the value of the switch. In the workshops, all we did was say if the past n samples are all 0, I'm going to say the outputs are 0, and if the past n samples were all a 1, the outputs are 1. But you don't actually have to do that. You can put on your digital signal processing hat and think in terms of filtering. I've actually described a very simple type of a filter, but there are other low-pass filters that you could have used and other things that you could have done. So the first thing is I just wanted to make you aware that there's more than one thing you can do. You can think of it in terms of filtering. We want to somehow low-pass filter that signal. So, well, I guess there's 3 questions. One is, how do you choose what filter to use? And I'll get back to that if I remember. How do you choose the clock speed? So for you guys, you're sort of stuck because the board has a 50 megahertz clock and people tell you to use that. But if it's your own design, you can choose the clock speed. Some of you may have discovered that you can actually create your own clock speeds because there are phase lock loops inside your FPGA that can be used to change the clock frequency. And beyond the clock frequency, you then have to ask, well, how many samples do I look at before making a decision about whether the switch is a 0 or a 1. So as a starting point, we need to, intuitively, if we think about it, remember that when I press that switch it might bounce a few times. We first of all want to understand what's the fastest rate at which it can bounce. Because if it can go up and down super fast and I only sample it here and here and here, I might by accident sample it every time it's a high and not even notice that it's oscillating. So in order to be able to effectively debounce it, I want to be able to see that it oscillates. To be able to see that it oscillates, I need to be sampling faster than the speed of oscillation. You know about the Nyquist rate, presumably, so by default you should say, well, if I want to see something at frequency f, I have to sample at least at twice that frequency. So your starting point might be at least 2 times the fastest frequency you expect to see. But then often you want to leave a bit of room for error, etc. And it seems to me, and I'm not an expert, but it seems to me that the default rule of thumb is probably to sample at about 8 times of what's happening. They use that rule for an old communication protocol like RS-232 and whatever. So between 2 to 8 times is probably sensible. 2 is probably a bit too small. 8 should be good enough most of the time. If you had to get away with 4, it'll probably work. So how do we apply this? Well, if there are 100 bounces in 1 millisecond, that suggests each bounce can be as short as 10 microseconds. So choosing a clock period at least less than 5 microseconds is probably what we should be doing to debounce that switch. And that means using a frequency of at least 200 kilohertz. You'll see that your 50 megahertz is well and truly fast enough to do what we want to do. Then how do I choose n? Well, of course, it depends on the frequency, because really n should be measured in units of time. So how long should we be observing the input before deciding whether the switch is a 0 or a 1? Because we're sampling it at the rising edge, we no longer think of the waveform as being a continuous time, so we count n with respect to the number of rising edges. If I double the clock rate, then I have to double n immediately to be able to sample the same amount of time as before. The larger n is, so what are the advantages and disadvantages? Well, the larger n is, the more I have to wait before deciding whether the switch has changed. That introduces more delay. The shorter n is, there's the chance that maybe the switch was just bouncing and I called it too early. Like most things in life, there is no one best answer. It really depends on your application. So ideally you should work out in your application what matters most. Does your application have to respond as fast as possible to this button press? Does the application have to be robust against thinking the switch was pressed when it wasn't, such as if it's the launch button? Obviously one takes priority over the other. It depends a bit on the application. And again, that's why we have engineers here to make educated decisions. So I've just told you that already. So one possible answer, so application specific, it could be that the application is such that we don't care if there's a delay. What we do care about is making sure that the switch really has been switched. Therefore, if we know that the longest that this switch can bounce for, the very longest is 1 millisecond, then we want to sample for at least 1 millisecond. And then given your clock period, you choose n so that n times the clock period is at least 1 millisecond, and off you go. That hopefully makes common sense. That hopefully is common sense. Another answer might be, because you're just designing some toy for someone, it doesn't really matter if it occasionally gets it wrong, is that you don't want to count so high. You don't want n to be large, because then you have to count that high, and that means you need lots of flip-flops. So you're willing to take your chances, and you might say, I'm prepared to assume that a button, if it's bouncing, will bounce at least 10 times per millisecond. Now, I don't know this for a fact, but I did say at the slide at the start that based on a quick Google search, switches supposedly bounce on average between 10 to 100 times. That we can assume that this is true at least most of the time. That means that the largest duration I need to watch out for is not 1 millisecond, but 1/10 of that. And so I can say, well, if the output's constant for at least 200 microseconds, then it should be safe to switch that switch. On the rare occasion that my switch doesn't bounce at least 10 times there, it might not work. But that's a chance I'm prepared to take because I need a cheap toy. It doesn't matter if occasionally it doesn't work. And so you get a different answer, and you save on the number of flip-flops. And if you're building 1 million products, suddenly saving even 1 cent matters a lot. Okay, the rest hopefully you've already worked out in the workshops. So I'm going to go through this relatively quickly. To implement the debouncer, everything's a finite state machine. So the first thing you do is work out, well, what is the state? Once you've done that, you then double check, can I write the output as a function of the state only? Because most of the time we want to build a Moore machine. And if I can't, I then have to go back and revise the state. The input comes from the actual switch itself. So this is in your workshop, so unless you have any specific questions about building a debouncer, I'm probably going to press the fast forward button. Oops, I didn't mean that fast forward. And so you end up with this code here. One thing that I want to point out, so in this small print here, we are using next counter like a variable in C. But I just want to emphasize today that that doesn't mean that next counter is going to be implemented as a variable, as a flip-flop. What happens is that we are describing in a C programming type of way what function I want to implement. So if I want to, I don't know, like the simplest function might be x, given x, return x plus 1. That's a function. How do you describe a function to someone? Or you can write down mathematically what it is. You can code it up in C and say someone, this is how you evaluate my function. What we're doing here is just describing programmatically a certain logic function. It doesn't mean it gets implemented that way. Roughly, I mean, this is very inefficient, but if you like, one way that Quartus could work, albeit very inefficiently, is this function, all it does is put in different possible inputs, computes the answer, and comes up with a truth table. And then, given that truth table, it goes off and implements that truth table using logic gates. That's the safest way of thinking what Verilog does. So never make the mistake that because you've got next counter equals counter plus 1, you're actually going to get this guy as a variable. It might not even appear in your final design. That's just a subtlety I wanted to point out to you today. Is probably a good time to have a reminder. You have to make sure that in this, so this is defining my next state. So my next state consists of next switch and next count, and I have to assign values to them in this green block no matter what. Because if I don't assign a value, it means it somehow has to remember its old value. And the only way to remember old values is to use a latch or a flip-flop, and hence you get that error message saying inferred latch, I can't do what you want, I'm therefore going to do something else. And if you don't read your warnings, your thing implements that something else, and you wonder why it's behaving like something else and not what you wanted. So if you ever have an if statement in there, be very careful, because if statements might mean that you forget to assign something to the different outputs. And outputs, or in combinational logic, that output has to exist no matter what. So make sure you assign it there. I'm going a bit quickly because I'm assuming this is revision, but feel free to raise your hand to stop me at any time. I think I've combined two lectures into one. So your homework is to answer this question. Given the code I gave you just before, I want you to think about what would happen if I connected my input pin directly to a push button without going through a double flip-flop synchronizer. So I've taught you about metastability just before. I'm now asking the question, will anything go wrong? And if something does go wrong, what will go wrong if this input here can change at any time it likes? So that's your homework, to try to figure out what's going to happen under that condition there. And I managed to get myself confused. I was thinking of tomorrow's lecture as well, where I was going to show you some other stuff. That looks like that concludes today's lecture. Okay, thank you.